Okay,
I, okay,
okay. Good
okay,
afternoon and welcome to the European Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Xiaomin Tang from the Heilongjiang University. The title of his talk is Toroidal Cluster Algebra and the Toroidal Grothendieck ring of a tensor category. Please.
okay. Dear colleagues from our world, good afternoon. I'm Xiaomin Tang from Heilongjiang University of China, and it's my great honor to present our joint work with Yu Zhang at this uh, seminar. Our research focus on the connection between toroidal cluster algebra and the toroidal Grothendieck ring of the tensor category and the full title as we see. First, let me briefly introduce the structure of today's reports. As we see, Uh, we will start with the background and motivation of the research, then move on to core topics like quantum affine algebras, class algebra, algebra with the multiple quantum uh, parameter, toroidal cluster algebra, and finally focus on the tensor subcategory Q and the toroidal quantum cluster structure attached to type A3. Now, let's begin with the first part, motivation. The cluster algebra were introduced by Fermi and Zaleski as a combinator device for studying uh, canonical basis and total positivity. They found immediately lots of applications, including the proof of conjecture of homologies concerning certain discrete dynamical system origin from the uh, Daniel base, and that's called Y system. Y system are strongly related with the representation theory of UQG G height. Y are the system of functions relation counts T system. See the paper of Kuniba, Nakanishi, and Suzuki. Let's see be a category of finite dimensional QG height module of type 1. That is, this module are also regarded as modules of the quantum loop algebra UQLG. Since quantum loop algebra can be revealed as the quotient algebra of quantum affine algebra by the two-sided idea generated by the central elements. Since UQG hat is the Hopf algebra, C is the abelian monoidal category, it's well known that C is not semi-simple. Let R be the Grothendieck ring of C. It was proved by Cherry and Bryson that simple objects S of C uh, are parameters by n types of polynomials of constant term 1, uh, the matrix P, or I equals 1 to n, and n equals rank G. The polynomials P are often called the Drinfeld polynomials because analogous result for Young's was obtained by Drinfeld. The representation VP is called at fundamental representation and denoted by VIA, APIU. equals 1 plus AU, and PG equals 1 for any J equal now equal I. We see a family of distinguishing the sample object of C is given by the Kirillov retangent module WKI whose Drinfeld polynomials are of the following form. Clearly, W1AI coincide with the fundamental module where A and W0AI is trivial representation for every I and A. The classes WKAI in R satisfy the following system of equation indexed by I, K, and A, called T system satisfy the following equations. Where the product runs over our vertex J adjacent to I in the Dunking diagram. The Q category homomorphism is the injective homomorphism Q from the Grothendieck ring of C to the ring of Laurent polynomial in infinite many variables Y. This homomorphism should be viewed as the Q analogy of the ordinary character homomorphism. The character of Ki module a solution of the T system, and this was proved by Nakajima at the following papers in the sample-less case and by Hernander in the generalist case. We can see the following two papers. It's easy to notice that in the sample-less case, the equations of the T system are exactly of the same form as the exchange relation is the cluster algebra. This slide, Hernander and like to introduce the cluster algebra structure on the Grothendieck ring of the 17 subcategories Ci of finite-dimensional QG height module by using the initial seed consisting of choose of n R plus 1 KR module in the following paper. The following sequence of monomial subcategories of C whose objects are characterized by certain strong rejection on the roots of the Drinfeld polynomials of their composition factors. For I equals 0, the class structure of R0 is trivial. There is a Yonki class consisting entirely of frozen variables. In papers of HL1, they found a cluster of algebra structure on R1 and prove it for G of type AN and D4. In the following two papers, Nakajima, motivated by the conjecture by Hernandez and Leclerc, Nakajima embedded the forming Celestin class algebra into the Grothendieck ring R of the category of representation of quantum loop algebras UQLG of a symmetric Cosmoti algebra studied early by the author, where private shifts on graded quiver vortices. In the second paper, Hernandez and Leclerc introduced Monoideal subcategories of the tensor category of finite-dimensional representation of a sample-laced quantum affine algebra parametered by arbitrary Dünke quivers. For linear oriented quivers of type A and D, they show that these categories put monoid categorification of cluster algebra of the same type. In the following paper, they dropped the assumption of being sample-laced and considered a much larger tensor subcategory, similar which contains up to spatial shifts. Other irreducible finite-dimensional representation of QG height. The first main result is the axiom which concludes the Q category of the arbitrary carrier taking module in C minus I as a result of the sequence of cluster mutations. If G is the sample-less type, in the first paper in following the T deformation T of the Grothendieck ring of the tensor category CZ of finite dimension UQLG module, they show that the T deformed Grothendieck ring KTQ of CQ is isomorphic to the positive part of the quantum enveloping algebra of G, and that the basis of class of same object of KTQ correspond to the dual of Lustig canonical basis, or CQ is the tensor subcategory of CZ. Sometimes this monoid subcategory CQ is called another likely subcategory for type Bn. Analogous CQBn were defined in the second papers, and the analogy of the isomorphism in the following third papers is explained in the papers. In the following first paper, the authors study the formation of cluster algebras with several quantum parameters called Toroidal Cluster Algebra, which naturally appear in the study of Grothendieck ring of representation of quantum affine algebra. They prove that the Toroidal Grothendieck ring of C1 of sample-less case has the natural structure of a Toroidal cluster algebra. The notion of a quantum cluster algebra with more than one quantum parameter also appear in the work of Goody Yakimu in the second and third paper, with the motivation related to study of quantum nilpotent algebras. In the following paper, Li and Pan, they focus on the correspondence between the conversation of the cluster algebra and the compatible Person structure on it, and leave this fact to non-commutative level so as to define a kind of quantum algebra with two parameters which are not trivial. And in this way, they can continue to discuss the possibility of high quantization. They call such algebra is a two-stage constant class algebra. Let us see the definition. The basis multi uh, parameter quotient torus tau is the algebra over Z T1 plus or minus 1 TR plus 1 or minus 1 with generator x1, x2, xn that cross commutator data is they are subject to the following relations or lambda a is my is a map from 1 to n multi itself to Z are skew symmetric maps. The matrix lambda A are the corresponding quotient commutation matrix. Tau is our dominant and its constant in its skew field of fractions f. The datum of lambda A is equivalent to the datum of R person brackets on the commutative polynomial ring ZXI. Have the following relation. We have the basis of the quantum torus given by commutative monomials. The following relation or UI are arbitrary integrals. We have the following definition. Toroidal seed in F is the collection S equals x1, x2, xn BQ'd lambda AS or xi in F are algebraically independent and quotient computed with quotient computation matrix denoted by lambda AS. The matrix BQ BIG is the skews symmetric n by m and for any a. We have the following equations where k is positive integers and 0 less m equals or less n. Now that this xi generated computer terms denoted by tau s and the generators xi are called toroidal cluster variables. For any a, BQ to lambda AS is a compatible pair in the sense of quantum cluster algebra. If R equals 1, it is quantum said. The variables xi are the quotient in the standard terminology of cluster algebra. We see the following definition. Let S be a toroidal seed for any k. The toroidal mutation in the direct k is as following: mu ks equals x1 sk plus 1 xc prime sk plus 1 xn b prime q ln plus as or b prime q obtained by the Euro mutation rule as follows. And we have the following product sk prime star product sk equal the right, or we have the following condition. Furthermore, the quotient commutative matrix lambda AS mutate according to the following formula. where Ek is a n by n matrix with the following in trace. The toroid mutation of a toroid seed in F is also a toroid seed in F. The mutation of the toroid seed is inverted. We have the following definition at S being a toroid seed in F. The toroid cluster algebra a tau S in F is the JT1 plus or minus 1 TR plus or minus 1 subalgebra of F generated by all toroid cluster variables of all toroid seed obtained by iterated toroid mutations. We have the following example. Let m equals 1, n equals 3, and r equals r. Let tau be the algebra over Z T1, T2 plus or minus 1 with generators x1, x2, x3 subjected to the following quotient commutative relations. Or lambda 1 and lambda 2 is for matrix as follows, and the light BQT equals 0, 1, minus 1. The collection S is the toroid seed. Since we have the following equations. We have the following two diagrams. Let S be a toroid seed in F. The associated toroid cluster algebra is contained in the T1 TR subalgebras of F generated by x plus or minus 1 xn plus or minus 1 and the second theorem is the quotient fit of Laurent expansion of every toroid class variables with respect to any toroid seed in a tau S are positive. Recall the keyword let Q be the orientation of the Dunking diagram of G. In other words, Q is the Dunking keyword of the same Dunking type as G. For in I, we denote by SIQ the keyword obtained from Q by changing the orientation of our every arrow with source I or tangent I. We have the definition let W be the reduced decomposition. It's the wire elements in wire group. We see that I is the adapted Q if I1 is the source of Q, I2 is the source of I, SA1Q, IK is source of these elements. There is a unique cluster elements having reduced the expression adapted to Q. We denote it by tau. A height function say from I to Z on Q is a function satisfying the following equation, or Q1 is a set for a row of Q. The following definition, the infinite repetition quiver Q height attached to Q is defined as the oriented graph with vertex set I height is pi iq satisfies the condition and two types of the following arose due to the time reason we I don't want to give the details of calculation here. The following relation I don't want into the details of calculation here. Here the example like Q being a skews serves dunking quiver of type A3 at 1, 2, 3 from 2 to 1, 2 to 3 and high function to be cos A1 cos A3 equals 2 cos A2 equal 3. The infinite repetition quiver Q height is shown in the left side of the following figure. Next, let CZ be the matrix with entries. CIGZ equals the right equation, or Z is the in the terminator. The C1 is just the Cardan matrix of G since data C it's not zero. This CZ is not zero. And C due to Z be the inverse of the matrix CZ. This is a matrix with entries Cij queued in QZ. The entries of Z due to Z high power series expansion in Z of the following form. Let Y be the Laurent polynomial ring generated by the correction of combinated variables YIR. Let U be the group of rational fraction of the form PZ divide QZ or PZ and QZ Q0 and the zeros of QZ are the unity. Give R in U, we can write the of course we can see the following paper for details. For any R in Z, we have the coefficient map pi R, so that we have the following equation. Next, we use the thousand TM for TZM, where I'm in Z. Let we do the infinite bigger algebra with generators YIR plus or minus 1 and constant commutation the following relations, where the map is given by the following two equations. This is the quantum terms of infinite rank. Recall that bijection phi from I height to that height define IQ height satisfies the following equation. And the light y infinite q due be the ZTR are in U, a sub-algebra of y infinite due generated by the YIP plus or minus 1 for IP in IQ. This is quantum torus of rank R equals the plus we have an example. We take G of type A3 and choose Q height as in example. The above example comparing the two curves in figure 1, we see that y infinite q is generated by the following 6 elements. Let y infinite be the equation of quantum torus y due to infinite by the following relations. Rk 1 equals the right element. Since y infinite q due is the subring of y infinite due, we have that y infinite q is the quotient of y due to infinite q by the relation Rk. The above relations. Next, write YIR instead of YIQR as omega I following the papers by Franco and rethinking FR for IR in I height, we introduce the following quantum of fine analogy of E of I as the following form. For I in I, let Ki infinite Q due be the algebra of y cubed infinite generated by the elements as following, where for I in I are in Z, not that. We have the equation, the following equation. Let chi r infinite be the image of chi I due infinite in y infinite. We have the following definition. The Toroidal Grothendieck ring is as follows. And the equivalent classes VIQR, Q infinite generator, chi infinite CZ as the algebra. We can see the papers of each for detail. Of course, we have the details of the calculation here. We due to the time, I don't see here. We have the following remark. Note that our fundamental modules are thin for type A, B, C, and G2. That is, their Q characters are multiplicative free. In fact, if fundamental modules are thin, their Qt character coincide with the usual Q character. Following this approach, the Q infinite character of any fundamental module via as follows. Then the Q infinite character of the same object Rm in CQ contains in general many monomials and prime which do not belong to Y infinite Q. By discarding these monomials, we obtain the truncated Q infinite character. We shall denote by Rm due to Q infinite the truncated Q infinite character of Rm. By example, the above 3.2, we can deduce that the relation between the truncated Q infinite character only involves two kinds of exponents, NA I0 J1 and NA I0 J2. All these exponents vanished for S equals or less minus 3. This implies that the parameters Ts with T equals or less minus 3 do not account in the relations describing the quantum toroidal Grothendieck ring of CQ corresponding to type A3. Following definition, we take the specialization that is TA 1 divided 1 A0 for a greater than 0. It is easy to see that the specialization are well defined. Under this specialization, it implies that T minus 2s equals T minus 2 for all s equals or less than 2, but the parameters T minus 2 s do not account. We have a interesting toroid structure with 2 in the patent deformation parameter T0, T minus 1, minus 2. We set the inverse of T minus 2 equals T. There we have the toroidal Grothendieck ring chi infinite CQ of type A3 generated by the following 6 elements, and the six elements have the following forms. We have the following proposition in that is in chi infinity CQ of A3 with the specialization for every IP in I hat Q and K equals 1. There hold the following equation. The following equation. or alpha ik and beta ik uh, satisfy uh, the relation. Now that the equation force is called toroid T system. Now we take I equals uh, mm, the vector have the elements 2, 1, 3, 2, 1, 3, and the cluster elements W equals S2, S1, S3, S2, S1, S3. It is easy to know the I uh, is adapted to Q. Following this isomorphism, we will set x1, x2, x3, x4, x5, and x6 satisfy have the following form. By the following paper uh, by Gerber Lacquer and so the mutation matrix B delta is given by I. By definition, to the two I s equals x1, x2, x3, x4, x5, x6 be delta lambda t0, lambda t is the toroid seed. We have the following theorem. The toroid cluster structure under toroid Grothendieck ring a chi-infinite skew of type A3 is a two-parameter quantum cluster algebra with the parameters T0, T and the toroid seed S. It's in the morphic to UQ plus, where UQ plus is a subalgebra of the multi-parameter quantum group UQSL4. Unfortunately, it is not isomorphic to the URSN that it is a two-parameter quantum groups as in the following paper by Hu and Pei. Finally, we have the corollary. The toroid cluster structure under toroid Grothendieck ring chi-infinite CQ of type A2 with the same specialization is isomorphic to the toroid cluster algebra in example uh, as above, corresponding to 0 and t. Similarly, it's isomorphic to UQ plus, where UQ plus is the subalgebra of the parameter quantum group UQSR3. Lucky it's isomorphic to the USN2. To summarize, we have the following works. First, we extended the cluster algebra frameworks to multi parameter toroid settings. Secondly, we likened toroid cluster algebra to the Grothendieck ring of the tensor subcategory CQ. Thirdly, we explicitly constructed the toroidal quantum cluster structure on K infinity CQ for type A3 Wolfram key isomorphism. This work opens up direction for future study, like extending to other dunking types or exploring applications to integrable system. Finally, I would like to thank my uh, collaborator Yu Zhang, the arranger of the European now Associated Algebra Seminar, and all of you for your attention. If you have any questions, please feel free to ask. Thank you for listening.
Thank you for your interesting talk. Are there any questions?
Thank you.
Comments or remarks? Let me see in the chat. Okay,
Okay.
I cannot see any questions, so let's thank the speaker again. And okay, we will resume on next Monday at the usual time. Thank you very much. Bye bye.
Okay, thank you. Bye.